Get started with chapter 8. Okay. So statistical tests are what we use a lot of the times. It's pretty much what we've built up to by this point. You had to know a lot of the vocab and stats right now from your past chapters to be able to do chapter 8. We're going to understand the rationale for statistical test, identify the null and alternate hypothesis in a statistical test, identify right-tailed, left-tailed, and two-tailed test, and use a statistic to compute the p-value. Now, I will let all of you know that when I was in your shoes taking stats for the first time at a lower level before grad school, null and alternate hypotheses are probably one of the hardest things to wrap your mind around in statistics. It's not so much hard in the sense of what you have to do. It's just hard in the sense of like, you have to know which is which. So sometimes they'll give you like a whole paragraph or 2 paragraphs worth of information, and you have to sit there and try and tease out what the null is and what the alternative is. And it can be a little bit difficult for sure. And then we're going to recognize types of errors, level of significance, and power of a test. So that means kind of like how good the test is. Like, can it be replicated in that kind of sense? So like, there are definitely some tests out there that are more meaningful and powerful than others. And then understanding meaning and risk of rejecting or not rejecting the null hypothesis. So sometimes when you have a null hypothesis, the main point is to figure out if you're rejecting it or not rejecting it. When you reject a null hypothesis, that's basically you saying that you are statistically confident enough to say that you were wrong initially and you are rejecting the original thought. Not rejecting the null is that you are, of course, standing by what you said. You now have data to back it up, and you're saying that your original hypothesis was correct. Okay. Introduction to statistical test. We emphasize the fact that one of the statistician's most important jobs is to draw inferences about populations based on samples taken from the population. Most statistical inferences center around parameters of population, often the mean or probability of success in a binomial trial. Okay. So methods for drawing inferences about parameters are 2 types. Either we make decisions concerning the value of a parameter, or we actually estimate the value of the parameter. When we estimate the value or location of a parameter, we are using methods of estimation. Decisions concerning the value of a parameter are obtained by hypothesis testing. The document or the topic we will study in this section. Okay. Wow, this is just super long. So I'm going to get us to an example. You guys can pause this as you need to read through it. Okay. Hypothesis and stating them. Okay. So your first step is to always figure out kind of what you're working with. So you want to read what's going on, and then you're basically going to pretend like whoever's going to read what you're writing has no idea what's going on. So you have to create what's called an hypothesis, and when it's your first one, it's your null hypothesis, and it's denoted by the H sub 0. The 0 obviously is another word for null, so that's why you use it. The value specified in the null hypothesis is often a historical value, a claim, or a production specification. For instance, if the average height of a professional male basketball player was 6.5 feet 10 years ago, we might use a null hypothesis of mu equal to 6.5 feet for a study involving the average height of this year's professional male basketball players. So that doesn't necessarily mean that you're going to get an average of 6.5 feet, but it just kind of means like, well, in the past, this is what happened. So I'm fairly statistically confident that it could still be happening. More likely than not, you're going to see kind of an increase. But I mean, that's what you would end up finding in your study. Okay, so as you collected the data, you would be able to decide if you're going to reject or fail to reject. Okay, if television networks claim that the average length of time devoted to commercials is 60-minute in a 60-minute program is 12 minutes, we would use the mean equal to 12 minutes as our null hypothesis. These examples are kind of straightforward to you. They are not always going to be, so please be careful in your homework and in your quizzes. This PowerPoint is not really setting you up to realize how difficult these can be. If they are this easy, then that's awesome for you, and I will obviously hear about that the next time we have class. Any hypothesis that differs from the null hypothesis is called an alternate hypothesis. An alternate hypothesis is constructed in a way that it is the hypothesis to be accepted when the null hypothesis must be rejected. So basically here, if we go back to the basketball player, you can see that the first null hypothesis, which is H sub 1, would be that the mean will be greater than 6.5 feet. Okay. Honestly, that's where my brain would have went to begin with, but I guess we'll see maybe down the road what's going to happen. So here you will want to pause the video and take down these definitions. Okay, so the null hypothesis, typically written as H sub 0. This is the statement that is under investigation or being tested. Usually the null hypothesis represents a statement of no effect, no difference, or in other words, things haven't changed. So if you think back to the basketball statement, it said that 10 years ago, the average was 6.5 feet for a male basketball player. 10 years is a long time. You know, these basketball players could be having different regimens. They could be having different diets. They could just be taller, you know, so there's a bunch of things that could have changed. But in your null hypothesis, you're thinking that maybe things haven't changed. Okay. So that might be a good idea or a good way to look at it. And it might help you when you're creating these for your homework and quizzes. Alternate hypothesis, H sub 1. This is the statement you will adopt in a situation in which the evidence or data is so strong that you reject the null hypothesis. A statistical test is designed to access the strength of the evidence or data against the null hypothesis. Here's our first example. A car manufacturer advertises that its new subcompact models get 47 miles per gallon. Let mu be the mean of the mileage distribution for these cars. You assume that the manufacturer will not underrate the car, but you suspect the mileage might be overrated. What shall we use for the null hypothesis? So if you go back to what you're given, the only thing you're given is 47 miles per gallon. So that's all you have to work with for your null hypothesis. So if you think, and here's what's going to help you with your alternate. Do you see here how it says, but you suspect that the mileage might be overrated? So that means that when you do your alternate, you would have a mu less than 47 miles per gallon, okay? So here we assume that they're correct. Here we're going to assume that we are less. And honestly, we're going to, because you feel so strongly about that, you would almost want your data to say that you want to reject the null and accept the alternative. Okay. All right. Types of test. The null hypothesis always states that the parameter of interest equals a specified value. The alternate hypothesis states that the parameter is less than, greater than, or simply not equal to the same value. Okay, so this is something that's super important. You will never pick your own number. So you might have to sometimes find it. So they might give you the data and you have to find the mean, but you're not going to just say, okay, well, if I'm given a mean of 47, in my alternate, I'm going to pick something different than 47. No, you pick how it relates to the 47. Okay. All right. When we're talking about types of statistical tests, this is what we're talking about. A statistical test is left-tailed if h sub 1 states the parameter is less than the value claimed in h sub 0. Okay, so it's skewed to the left, or actually skewed to the right. Sorry, I always get those backwards. Right-tailed if h sub 1 states that the parameter is greater than the value claimed in h sub 0. And two-tailed if h sub 0 states that the parameter is different from, in other words, not equal to the value claimed in h sub 0. Okay? Definitely go ahead and pause the video and write those down. You will want them. And I would suggest, if you are creating your exam note card or sheet of paper, whatever you end up having at the house, I would write this very small somewhere in some kind of shorthand so you have it. Okay. In this introduction to statistical test, we discussed tests involving a population mean. Okay, so it does tell you though here, however, you should keep in mind and be aware that the methods outlined apply to the testing parameters as well. So P, sigma, the combinations here, and so on. So table 8.1 shows you how tests of the mean are categorized. So again, you want to write this down at least in your notebook, if not on your note card. I would recommend your notebook, and then just kind of maybe highlight it so that if you're flipping through when you're getting ready for your final, you can go ahead and write that down. All right. Hypothesis test of mean given x is normal and sigma is known. Once you have selected the null and alternate hypotheses, how do you decide which hypothesis is likely to be valid? Data from a simple random sample and the sample test statistic, together with the corresponding sampling distribution of this test statistic, will help you decide. All right, so let's look at example 2, which we are not there yet, apparently. You guys can read this for yourselves. And again. Okay, here's our procedure. So first off, the requirements. Now remember, the requirements are the part in your quiz, homework, or exam that will end up probably being multiple choice. So the X distribution is normal with known standard deviation. Then X bar has a normal distribution. The standardized test statistic is followed. So Z is equal to X bar minus mu over sigma divided by the square root of n. Okay, you've seen this before. All right, let's look at example 2. Rosie is an aging sheepdog in Montana who gets regular checkups from her owner, the local veterinarian. Let X be a random variable that represents Rosie's resting heart rate in beats per minute. From past experience, the vet knows that X has a normal distribution with sigma equal to 12. If the vet checked some kind of vet manual and found that for dogs of this breed, the mean should be 115 beats per minute. Okay. over the past 6 weeks, Rosie's heartbeat measured 93, 109, 110, 89, 112, and 117. So here is a great example that they are giving you a data set that you will have to find the mean, but then you will still use the mean. You're not going to pick like another random number. The vet is concerned that Rosie's heart rate may be slowing. Does the data indicate that this is the case? Okay. So establish a null and alternate hypothesis. So again, we're going to go with the 115, which was found in that vet manual. Okay. The X bar we're going to use in a minute whenever we do the test statistic. The null hypothesis then is mu equal to 115. The alternate is mu less than 115 because he's worried that her heart rate is slowing. Okay. Then it wants to know, are the observed sample data compatible with the null hypothesis? Are the 6 observations of Rosie's heart rate comparable or compatible with the null hypothesis? So to answer the question, we need to know the probability of obtaining a sample mean of 105 or less from a population with a true mean of 115. Okay. So how do you calculate the probability? All right, so first you had to find X bar, which you already did. Figure 8.1 shows the distribution and corresponding standard normal distribution with desired probability shapes. So here's our p-value. Okay, they've already done the z-score for you, but you would have to do that on your own. Okay. All right. Figure 8.1 is obviously very important to you. So we have to check the requirements. Since X has a normal distribution, X bar will also have a normal distribution and for any sample size n and given sigma. Note that using mu equal to 115 h sub 0 from h sub 0 and sigma equal to 12, our n is 6, and that's obviously from the data, and we figured out the X bar from the data as well. So now you just got to plug everything in. Okay, that's where that 2.4 came from in the slide before. All right. Using the standard normal distribution table, we find the following. Oh, a little too fast, sorry. Okay. So, that's like, what, 2.1%? Yeah. What conclusion can be drawn from Rosie's average heart rate? Since the X bar is less than or equal to 105, is only about 2%. Because this probability is very small, we reject and conclude that H sub 1 mu less than 115, Rosie's average heart rate seems to be slowing. Okay, so basically, even though some of her heartbeat rates are less than 115, overall she is not decompensating. She's not losing her heart muscle. All right. Have we proved this to be false? Have we proved the null to be false and the alternative to be true? No, the sample data does not prove. I don't know who wrote this. Obviously, there's some English errors. The sample data does not prove that the null hypothesis is false and that the alternative to be true. We do say that H sub 0 has been discredited by a small value, p-value. Therefore, we abandon the claim and adopt the following. Okay. Right. This is very important here. This p-value, you will be asked it over and over and over again. All right. The p-value of a statistical test. That you can definitely pause and write. Right. Assuming H sub 0 is true, the probability that the test statistic will take on values as extreme or more extreme than the observed test statistic computed from the sample data is called the p-value of the test. The smaller the p-value computed from the sample data, the stronger the evidence against the null hypothesis. All right. The p-value, sometimes called the probability of chance, can be thought of as the probability that results of the experiment due to only chance. All right. The lower the p-value, the greater the likelihood of obtaining the same or very similar results in repetition of statistical experiment. Okay, so those are all good things. Thus, a low p-value is a good indication that your results are not due to random chance alone. The p-value associated with the observed statistic takes us on different values depending on the alternate hypothesis and the type of test. Okay, so let's look at some more examples. Well, you can go ahead and write that down. Okay. And this will also be good for your note card for your exam. Again, if I'm going too fast live, you can always pause it later. Okay. Types of errors. If we reject the null hypothesis when it is in fact true, we have made an error that is called, a type 1 error. On the other hand, if we accept the null hypothesis when it is in fact false, we have made an error that is called a type 2 error. Table 2 indicates how these errors occur. Please write down and pay attention to this table. Again, I'm trying to help you from experience. The type 1 and type 2 errors when I was a student, definitely something that I totally guessed on. For whatever reason, my brain could not comprehend it. I don't know if it was how my teacher taught it. I don't know if it was just because by that point in the semester or year, I was just kind of tapped out. I have no idea. But the type 1 and type 2 errors always gave me trouble. Maybe it has something to do with my dyslexia. I don't know. But these were very hard for me to understand. So if you guys can get them better than I did, that is fantastic. And I will be so happy and thrilled to see that you were successful in that. Okay. All right. Types of errors, you guys can read about this on your own. Just pause it, take it down mentally, or if you want to write it out, you can write it out. I don't feel like you'll need to write any of this written down for your note card. One thing you do want to take note of is where it says the probability with which we are willing to risk a type 1 error is called the level of significance of a test. The level of significance is denoted by the Greek letter alpha, and it doesn't really look like an A. It looks more like this. Okay. All right. Again, go ahead and pause and write all this stuff down. The level of significance there, it's written correctly. Alpha is the probability of rejecting the null hypothesis when it is true. This is the probability of a type 1 error. The probability of making a type 2 error is denoted by the Greek letter beta. Methods of hypothesis testing require us to choose alpha and beta values to be as small as possible. In elementary statistical applications, we usually choose alpha first. So it's kind of like alpha is a P and beta is a Q, but you definitely want to use the letters alpha and beta, okay? You cannot use the letters P and Q and expect someone to understand that you're talking about type 1 and 2 errors. The quantity 1 minus beta is called the power of a test and represents the probability of rejecting the null hypothesis when it is fact true or false, sorry. All right. For a given level of significance, how much power can we expect from the test? The actual value of power is usually difficult and sometimes impossible to obtain, since it requires us to know the H1 distribution. However, we can make the following general comments. Okay. The power of a statistical test increases as the level of alpha significance A increases. They flip-flop those A's around. Sorry. A test performed at the alpha equals 0.05 level has more power than a test performed at 0.01. The reason for that is because the confidence interval that's related to alpha of 0.05 is 95% confident. That doesn't make sense because then this would be 99%. We'll get to that. We'll figure it out. This means that the less stringent we make our significance level alpha, the more likely we will be to reject the null hypothesis when it is false. Okay. Using a larger value of alpha will increase the power, but it will also increase the probability of a type 1 error. Despite this fact, most business executives, administrators, social scientists, and scientists use a small alpha value. This choice reflects the conservative nature of administrators and scientists who are usually more willing to make an error by failing to reject a claim than to make an error by accepting another claim that is false. Again, I cannot stress how much you need to pay attention to the tables in this chapter. Table 8.3 summarizes the probabilities of errors associated with statistical tests. Make sure you pause the video and take this down. All right. Concluding at statistical test. Usually alpha is specified in advance before any samples are drawn so that the results will not influence the choice for the level of significance. To conclude a statistical test, we compare our alpha value with the p-value computed using the sample data and the sampling distribution. Procedure: how to conclude a test using a p-value and a level of significance alpha. If p-value is less than or equal to alpha, we reject the null hypothesis and say the data are statistically significant at the level alpha. If the p-value is greater than alpha, we do not reject the null hypothesis. Again, pause the video, write it down. You will need to use this technique over and over again. Okay, basic components of a statistical test. A statistical test can be thought of as a package of 5 basic ingredients. Here are the first 2. Null hypothesis, alternate hypothesis, and preset level of significance alpha. Number 2, test statistic and sampling distribution. I will give you a few seconds to pause so that you can write all the detail down that you are personally needing. All right, number 3, p-value. All right, we all know what this is at this point, but again, you can pause the video and write it down for yourself. Test conclusion is number 4. And of course, number 5, the part that you guys are really missing out on by us having to be online, and I will try to find some kind of project for you, interpretation of the results. All right, this is the part where you're actually writing up your report and you're figuring out what you want to tell your boss about the situation. Okay, again, pause the video and write this down. Okay. In most statistical applications, the level of significance is specified to be alpha 0.05 or alpha 0.01. You can use other values, but at the vast majority of times, you're literally just going to see that. You're not going to see like a weird alpha equal to, I don't know, 0.125. It's just not going to happen. Then we say that we are using 5% level of significance. This means that in 100 similar situations, H sub 0 will be rejected 5 times on average when it should not have been rejected. Using technology at the end of this chapter shows a simulation of this phenomenon. When we accept or fail to reject the null hypothesis, we should understand that we are not proving the null hypothesis. We are saying only that the sample evidence, the data, is not strong enough to justify rejection of the null hypothesis. Okay, so the word accept sometimes has a stronger meaning in common English usage than we are willing to give it in our application of statistics. Therefore, we often use the expression fail to reject instead of accept. Okay. All right, 8.4, fail to reject simply means that the evidence in favor of rejection was not strong enough. Okay. It's a very, very long section. Often in the case that H sub 0 cannot be rejected, a confidence interval is used to estimate the parameter in the question. The confidence interval gives the statistician a range of possible values for the parameter. All right, finally, we are done with that one. Okay, 8.2, testing the mean. You guys can take a look at that for yourselves. All right, in this section, we continue the study of testing the mean. The method we are using is called the p-value method. You can read a little bit about its history there. Okay, so we literally just went over the section. I'm not going to reread anything to you. You guys can kind of read that on your own if you have paused the video to come back to it. Okay. All right. Okay, knowing the sampling distribution of a sample test statistic is an essential part of hypothesis testing process. For students of mean, for test of mean, we use one of the two sampling distributions for X bar, the standard normal distribution or the student's T distribution. The appropriate distribution depends upon our knowledge of the population, standard deviation, the nature of the X distribution, and the sample size. All right, part 1. Testing mean when sigma is known. So that must mean we also have to do it with sigma unknown. In most real-world situations, sigma is simply not known. However, in some cases, a preliminary study or other information can be used to get a realistic or accurate value for sigma. All right, go ahead and pause the video so you can write down the procedure. Some of you may want to just play around with it first, maybe do some shorthand. It's a lot of words there. Okay. This one you can probably write the whole way out. It's not nearly as wordy. All right. We have examined p-value tests for normal distributions with relatively small sample sizes and less than 30. The next example does not assume a normal distribution, but has a very large sample size. Sunspots have been observed for many centuries. Records of sunspots from ancient Persian and Chinese astronomers go back thousands of years. Some archaeologists think sunspot activity may somehow be related to prolonged periods of drought in the southwestern United States. All right, so this is the information that was gathered. It's a random sample of 40 such periods from Spanish colonial times gave the following data. Okay, so obviously you would find your X bar. And yes, of course, you could use a calculator or Excel or Google Sheets to do so. All right, so the sample mean, the X bar that they get is 47.0. Previous studies of sunspot activity during this period indicate a sigma of 35. It is thought that for thousands of years, the mean number of sunspots per 4-week period was about 41. Okay, there's your mean. So that's what you're going to use for your null hypothesis and your alternate, okay? Sunspot activity above this level may or may not be linked to gradual climate change. Does the data indicate that the mean sunspot activity during the Spanish colonial period was higher than 41? Use an alpha of 0.05. So you see here that they're basically being given the alpha, okay? So if you as a statistician is coming up with a situation, then you want to pick the alpha early, okay? All right. Example 3, establish the null and alternate hypothesis since we want to know whether the average sunspot activity during the Spanish colonial period was higher than the long-term average of 41. So here again, we are using 41. We didn't make it up. We didn't pull it from the data. That's where we got it from, and we're good. All right, check the requirements. What distribution do we use for the samples test statistic? Compute the test statistic from the sample data. Since n is greater than or equal to 30, we know sigma, we use the standard normal distribution. We're given the X bar, we were given sigma, we were given mean. We know that n is 40, so you plug everything in. And you get a z-score of 1.08. Okay, there's drawing. They went ahead and figured out their p-value already. So if we conclude the test, since the p-value is 0.1401, which is greater than 0.05 for alpha, we do not reject the hypothesis, sub-zero. This means that we interpret the results in the context of the problem. At the 5% level of significance, the evidence is not sufficient to reject the null hypothesis. Based on the sample data, we do not think the average sunspot activity during the Spanish colonial period was higher than the long-term mean. Okay. We have about 20 minutes left, so, and we're about halfway through this, so I am going to stop the video after this section, but then I will make a new video, and that will be the second part of chapter 8, sorry. Part 2, testing mean or mu when sigma is unknown. All right. You guys can read this to yourself. Of course, we know that most of the time we're not going to know everything, especially in real world situations. Again, pause the video, write down your procedure. I would recommend using some shorthand here, unless you really like writing, then you can write it all out. All right, again, here is your procedure. You can see we're going to end up using our t-test instead of using our, instead of using the one with the z. Okay. Again, you guys can read this information. Table 6 out of Appendix 2, super important for you. You have to figure out if you need a one tail, two tail, or Yeah, one or two-tailed will get you different answers. All right. Note, in table 6, areas are given in one tail beyond positive t on the right or negative t on the left, and in two tails beyond plus or minus t. Notice that in each column, two-tail area, 2 times the one-tail area. Consequently, we use one-tail areas as endpoints of the interval containing the p-value of a one-tailed test. All right, you will understand that a little bit more when we go through an example, and definitely when you're working through your homework. I would highly recommend writing these down again. The more often you write it down, the more likely it is you will be able to memorize it. Example 4 shows how to use Table 6 of Appendix 2 to find the interval containing the p-value corresponding to a test statistic t. Again, here we have some information, some data that was collected from the Texas Cancer Center. You want to find your sample mean, which is X bar, which is 17.1 weeks, with a sample standard deviation of S equal to 10. We're going to let X be the random variable representing the remission time in weeks for all patients, okay? And we have an N of 21. Assume that the X distribution is mound-shaped and symmetric. A previously used drug treatment had a mean remission of 12.5 weeks. Does the data indicate that the mean remission time using the drug CMP is different either way from 12.5 weeks? Use an alpha of 0.01. You will find in a lot of cases, especially with medical stuff, that they will use an alpha of 0.01. Establish the null and alternate hypothesis, since we want to find if the drug provides a mean remission time that is different from the provided 12.5 weeks. All right, check requirements. You guys know how to do all this. This is just kind of like putting everything together from the last chapter. All right, so your T is going to be 2.108. Go ahead and draw it all out here. Again, if you've been working along with everything, you should be more than fine on doing this. Since this is a two-tailed test, we use entries from the row headed by two-tail area. Look up the t-value in the row headed by degrees of freedom n-1, so we know we have 20. The sample statistic t equals 2.108 falls between 2.086 and 2.528. So the p-value falls between 0.050 and 0.020. All right, see table 8.5. Okay. I suggest you actually go into the appendix. Don't just take this little snippet as your table. Actually go look at table 8.5 and figure out how to use it. Conclude the test. The following diagram shows the interval that contains the single p-value corresponding to the test statistic. Note that there is just one p-value corresponding to the statistic. Table 6 of Appendix 2 does not give that specific value, but it does give a range that contains the value. As the diagram shows the entire range is greater than alpha, this means that the specific p-value is greater than alpha, so we cannot reject the hypothesis. Sorry, the null hypothesis. If you have to draw that out, go ahead and do it. I don't mind what your work is. Using the raw data computer software gives p-value equal to roughly 0.048. This value is in the interval, so we estimated. It is larger than the alpha, so we do reject the null hypothesis. Interpretation. Interpret the results in the context of the problem. At the 1% level of significance, the evidence is not sufficient to reject the hypothesis. Based on the sample data, we cannot say that the drug provides a different average remission time than the previous drug. All right. Part 3, testing mu using critical regions, the traditional method. Again, if you need to pop off of here because we're getting close to time, that's fine. But I am going to finish this out. So, and then you can look for both parts up on Canvas later today. The most popular method of statistical testing is the p-value method. For that reason, the p-value method is emphasized in this book. Another method of testing is called the critical region method or traditional method. For a fixed preset value of the level of significance alpha, both methods are logically equivalent. Because of this, we treat the traditional method as an optional topic and consider only the case of testing mu when sigma is known. Okay, so they're not going to go through both options here for you. I'm sure you could probably look for it in another textbook or online, but either way, you're not going to be asked about it. So it would just be for personal knowledge. Consider the null hypothesis mu equal to k. We use information from the random sample together with the sampling distribution for x bar and the level of significance alpha to determine whether or not we should reject the null hypothesis. The essential question is, how much can x bar vary from mu equal k before we suspect that the null hypothesis mu equal k is false and rejected? All right. The answer to the question regarding the relative size of x bar and mu, as stated in the null hypothesis, depends on the sampling distribution of x bar and the alternate hypothesis h sub 1 and the level of significance alpha. If the sample statistic x bar is sufficiently different from the claim about mu made in the null hypothesis, we reject the null hypothesis. The values of x bar for which we reject h sub 0 are called the critical region x bar of the distribution. All right, those should look kind of familiar to you. Go ahead and write them down anyway, because they are being used a little bit differently here. Depending on the alternate hypothesis, the critical region is located on the left side, the right side, or both sides of the x bar distribution. 8.7 shows the relationship of the critical region to the alternate hypothesis and the level of significance alpha. Notice that the total area of the critical region is preset to be the level of significance alpha. This is not the p-value discussed earlier. In fact, you cannot set the p-value in advance because it is determined from a random sample. We know that the level of significance alpha should, in theory, be fixed, preset number assigned before drawing any samples. Okay, again, we talked about this before. Alpha of 0.05 and alpha of 0.01 are your most common. You could have other ones. You yourself could pick other ones, but that's kind of very rare. And for conventional reasons, you almost always use 0.05 and 0.01. Again, you can pause the video and write this all down if you want. I would definitely write this down. This is if you're going to write anything out of any of these things down, any of the slides, whatever, any of the notes, documentation, I would write down all of the little diagrams and tables. Those are going to help you the best. Again, go ahead and pause this. This is using critical regions. Okay. All right. For easy reference, they are also included in Table 5 of Appendix 2, Areas of Standard Normal Distribution. The procedure for hypothesis testing using critical regions follows the same first two steps as the procedure using p-values. However, instead of using a p-value for the sample test, we check if the sample test falls in the critical region. If it does, we reject the null hypothesis. However, we do not reject Otherwise, we do not reject the the null hypothesis. Sorry, the H sub 0 made me think it said however. All right. Again, here you have a really long procedure. I would definitely write it in shorthand, but that's me. Okay. Here's an example. Consider example 3 regarding sunspots. Let X be a random variable representing the number of sunspots observed in a 4-week period. A random sample of 40 such periods from the Spanish colonial times gave the number of sunspots per period. The raw data are given in example 3. The mean was 47.0, and previous studies indicated that for this period, sigma was equal to 35. It is thought that for thousands of years, the mean number of sunspots per 4-week period was about 41. Does the data indicate that the mean sunspot activity during the Spanish colonial period was higher than 41 using alpha of 0.05? So we're going to set the null hypothesis and the alternate hypothesis as an example 1. We're using the same. Sorry, the first time we did this in example 3. You're going to compute the sample statistic as in example 3. We use the standard normal distribution with, and then you'll just plug it in. And we get the same. Okay. All right, determine the critical region and critical value based on H sub 1 and alpha equal to 0.05. Since we have a right-tailed test, the critical region at the rightmost 5% of the standard normal curve, according to figure 8.8, is the critical value Z sub 0, 1.645. You should know that from past exam. Conclude the test. We conclude that the test by showing the critical region value and sample statistics Z 1.08 on the standard normal curve. All right, there you go. That should be old hat to you at this point. We can see the sample statistic does not fall in the critical region. Therefore, we fail to reject the null hypothesis. Okay, so here's where it lands. Here's the critical region. All right. If you guys have to draw this out, don't be afraid to draw it out. I might even give you bonus on your test if you do. Interpret the results in the context of the application. At the 5% level of significance, the sample evidence is insufficient to justify rejecting the null hypothesis. It seems that the average sunspot activity during the Spanish colonial period was the same as the historical average. How do results of the critical region method compare to the results of the p-value method for a 5% level of significance? The results, as expected, are the same. In both cases, we failed to reject the null hypothesis. Here's your procedure. Make sure you pause and write it down. You guys can decide based on the quiz if you feel like you need this for your exam. Again, I will email out and let everyone know if the exam has majority 9 and 10 on it, or if it's a mixture. I'm pretty sure it's a mixture. So I would just be prepared for anything. All right. That is the end of